Okay, let's begin this session. The first talk is Maximum Entropy Distributions, Bit Complexity and Stability by Damian Strachak and Nishith Vishnoy, and Nishith is going to give the talk.
I told you to.
Do you want, do you-
I will do that.
okay. Welcome everyone to this session. So I'm going to be talking about a problem which appears in many different areas called the maximum entropy distribution, and talk about the computability of it, and in particular look at some of the more structural aspects of computability, complexity, and stability, which I'm going to tell you soon. And this is joint work with my student Damian Strachak. So here's the problem. So imagine that you're given a family of vectors. Think of them as 0, 1 vectors, if you like, a large number of them. And you're also given a point, theta, which is also in an m-dimensional space. And you can write this point in many different ways as a convex combination of these points in the family F. But in many areas, what becomes important is to find the entropy maximizing distribution, or a way to write this point as a convex combination of various vectors which are given to you, which maximizes the entropy of the distribution arising from this convex combination. So there's a very natural convex program that you can write. You create a variable q sub alpha for each point in the each point in the family F, and the point theta is inside the convex hull of these objects, and what you're looking for is an entropy maximizing distribution constrained to the fact that the average of, so summation q alpha alpha is theta. What that means is that the expectation over all the points F gives you exactly theta. So the problem is that the case that we are interested in is when the family F could be exponential sized and also implicitly specified. So you can imagine, for instance, F consists of all spanning trees in a graph, and the object that is given to you is not the collection of all the spanning trees, but the graph which implicitly captures all these spanning trees. And theta may be an average of observed samples. So for example, I give you n distinct spanning trees from some distribution, and your goal is to now construct a model of this distribution. So this is the setup. So the problem with this convex program is, in the setting when F is exponential, is that it has a lot of variables, and so it's not really feasible. And so one strategy is to move to the dual of this object, and the dual has m variables, and m variables because there are really m constraints corresponding to summation q alpha alpha equal to theta. So which is a nice thing. So this problem has a small dimension in terms of variables. It has two issues. One is that the sum inside the log is an exponential sum, which means that it has exponentially many entries. And so how do you compute that? And also it's an unconstrained optimization problem. So if you want to use convex programming to solve this convex optimization problem, we need a way to get a bound on where theta lies, or where the optimal solution y star lies, and also a way to evaluate the function or the gradient of this function. So both of them are non-trivial problems and relate to some important problems in theoretical computer science. But the focus structurally would be, given a theta and the polytope, how can we bound where this optimal solution lies? Also study the question of stability. Since this theta often is derived as an average of samples, there could be error, and so you want to understand if this is a model reasonable. If you perturb the theta vector a little bit, does the probability distribution change suddenly? And if it's so, then it's not a very useful way to model the problem that you're trying to model. So these are both questions which are motivating this work. And in terms of stability, what we are looking for is, if I have these two probability distributions, one corresponding to the first theta and the other corresponding to the second theta, in terms of total variation distance, how does it relate to the distance between the 2 points? And we would like this Lipschitz constant L to be as small as possible. So what are some of the issues and prior works in this problem? So one of the issues is that as this point theta gets close to the boundary of the polytope, necessarily y star, the optimal solution, goes to infinity. So you cannot really expect any bounding box. So remember, in the convex programming approach, you need some ball in which you can prove that the optimal solution lies. You cannot really hope that this holds. So with Mohit Singh in 2014 in a paper in Stock, we proved the following result, that if this point theta is deep inside the polytope, which means you can put a ball of radius eta around it and still the whole ball is inside the polytope, then you can prove an upper bound on the size of the optimal solution, which allows you to then give computational results. And a question that was open is whether we can show a similar result or something similar when theta can be anywhere. Now this question is not even well defined, because I just said that as theta goes to the boundary, this optimal goes to infinity. So what we really want is that, can we find a y star which approximates the optimal solution, but is close enough, lies in a polynomial radius around the origin for any point inside the polytope, including the boundary of the polytope. And this particular question has many applications. In particular, Avi will talk about it today, I think, about his work on Braskamp-Leib constants, Avi Vigdersen. It's motivated primarily from there, but there are also relations to convex counting problems and so on. And the way this is used in many of these applications is that there's an outside optimization problem, which is an optimization over the entire polytope. And because of this supremum outside, you really cannot guarantee the assumption that is required in this theorem with Mohit Singh. So you really need to know the bound on the optimal solution everywhere. So the main results of this paper are we basically resolve this problem to as much as one can. So assuming that the polytope has reasonable behavior, which means that in the description of the facets of the polytope, we don't use exponentially large numbers. So if every coefficient is an integer, we require that it's bounded by, let's say, some number m, which you think of as polynomial in the dimension. And then what we can show is that there's always a solution, which we call y star theta epsilon, for a given epsilon. So what does that mean? So this solution approximates the value of the dual up to an additive of epsilon. And it's bounded by a polynomial in m and log 1 over epsilon. So this is the right notion of bound that enables polynomial time algorithms for the problems mentioned in the previous application, previous slide. So in particular, we get the first polynomial time algorithm for computing Braskamp-Leib, rank 1, and so on. Surprisingly, or not so surprisingly, this bit complexity bound also implies and is intimately related to the stability result. The reason why the distribution turns out to be stable is because nothing really nasty happens as the point theta approaches the boundary of the polytope. And so this is an important technical proof which we derive from the proof of the bit complexity result. We also give a lower bound that this assumption on the polytope is necessary. We can construct polytopes where you can have very large bit complexity if you don't have this assumption. The proof is not difficult. It just relies on a careful analysis of the optimal solution. So you start by the optimal solution. Even though it lies at infinity, it has some direction. And our goal is to bring this, so identify a basis in which we can study this vector, so that if I now start truncating the point in that basis and pull this point back from infinity to somewhere in a polynomial ball around, the objective function doesn't change by more than an additive of epsilon. So that's really what goes on inside the proof. And here are some steps. I think time is not enough to explain all the steps. And yeah, so I have a minute. Let me also mention that this result works with weighted exponential sums in case you have a prior on the max entropy distribution and you're trying to find the KL divergence minimizing probability distribution with respect to this prior. And to end, I would mention that the lower bound example we have is a family of vectors where the coordinates of the vectors are not 0, 1. And one of the problems that remains open is, can we find a 0, 1 polytope which has this property that it requires a large bit complexity. And the second, I think, a more important, more interesting open problem is in the stability result, we had a square root. So the L1 norm of the difference of the two probability distributions scaled with the square root of the distance between the two vectors. And this is something I don't know how to remove for the class of polytopes I described. And this is a very nice open problem, and I would end with this. Thank you.